Welcome back to ECE 501B. Don't want to scare you, but there's quite a few announcements or due dates. One is today, that's homework 4, and then the next 2 Mondays are homeworks 5 and 6. Homework 5 you should be able to do now. It's chapter 5 material, and homework 6 gets into chapter 6, which is on the inner products. And exam number 2 is not too far away, and that's on the 4th of November. Wow. It's already the 19th of October. Today what I want to do is continue our discussion of chapter 6, which is dealing with the inner product, which when combined with a vector space gives us these inner product spaces. The inner product gives us a length, and it gives us an angle, or a sort of how close are these vectors to one another, where vector is not necessarily the traditional vector. But once we have this closeness, or angle, then we can speak of these vectors being orthogonal. And what we want to talk about today are a lot of these relationships that deal with vectors and maybe their relationships to one another. Given two vectors, can you say anything about the size of those vectors relative to the size of the inner product? Or what about the sum of those sizes of those vectors? And that's leading us then into CSI. We're not on a TV show, but that's the Cauchy-Schwarz inequality, and that deals with the product of the norms. And we can actually see that that now collapses down to providing us with an angle, a piece of angular information. If we start dividing both sides through by the norms of u and v, now we have a bound on this quantity between -1 and +1, and that's like the cosine of an angle. And if we define that to be the cosine of theta, now we have this angle of separation between these two vector quantities. The triangle inequality, so if you think of the Cauchy-Schwarz as a product of the norms, the triangle inequality dealing with two vectors, now we're looking at the sum of those two norms, and that is always exceeding the sum of the norm of the sum of the two vectors. That's the triangle inequality. Another equality is this parallelogram equality. Then we will start talking, once we have this notion of norms, which now we do with this inner product, that's how we were defining our norm, we can start normalizing our basis vectors. And a nice way to normalize them is for them to have a length of 1. Now we can create orthonormal basis, and we can actually develop a way to construct those, which is this Gram-Schmidt process of orthogonalization. So that's creating an orthonormal list. If you have a set of basis vectors, can you now create, via this Gram-Schmidt process, a way to orthogonalize those vectors and normalize so that you now have an orthonormal basis? That's where we're headed in chapter 6. As a summary of where we've come from, and actually sort of as a hint to where we're going, let me just summarize what we have done. We've created or defined an inner product, which is a way of taking two vectors from our vector space and creating a scalar. And that inner product needed to have certain properties. One property was positivity, which realized that that positivity is with the same vector. The inner product can give you a negative number. But if you have the same vector in both slots, the inner product better give you a non-negative value. And the only time when you have a 0 value is when that vector itself is the 0 vector. That's the definiteness property. We also wanted, or the inner product has an additivity in the first slot property, which means we can separate that sum in the first slot into two inner products. We also had homogeneity in the first slot, which now that allows the scalar to simply slide out in front of the inner product if it's buried inside the first slot as a scalar. And we had conjugate symmetry, which means if we interchange the slots with our vectors, we have to conjugate the result, meaning the inner product of uv is equal to the conjugate of the inner product of v and u. Some other consequences of the inner product: we defined a norm, which is simply the positive square root of the inner product of u with itself. We can see that if we have a vector scaled inside the norm, and here if we just square the norm, it makes it a little cleaner. We don't have to carry around a square root sign. Then we can utilize the information we know about homogeneity. We know that we have homogeneity the first slot and conjugate homogeneity in the second slot, which now allows us to slide those scalars out in front and have a scalar A times its complex conjugate out in front. But A times its conjugate just gives us the magnitude of A squared. So that if you now take the norm squared of AU, then that's the same or equal to taking the magnitude of the scalar A, squaring that, and multiplying that by u squared. The orthogonality concept is now available to us. If we have two vectors and they are orthogonal to each other, that means that their inner product is 0. And here is where we will start today, which is with orthogonal decomposition. This looks like a messy formula, but it's actually quite clean. And we will derive this formula, but we are essentially saying, what if we have two vectors, u and v? Can we decompose one of those in terms of the other and a vector orthogonal to the other? Meaning, suppose we take u and we say, decompose u, break u up into two pieces. One piece of the vector u we want in the direction of v, and the other piece of u we want to be orthogonal to v. That's what this orthogonal decomposition is telling us. We want to know how far do we go in the direction of v. That's this A that I'm saying is our scalar, and that's just the inner product of u and v over the norm squared of v. And that now scales. That's just a scalar. That's the component or the amount that we move in the v direction to try to decompose u. And then we have another component that's actually orthogonal. So this is the component of u that's orthogonal to v or perpendicular to v, and we'll call that w, and that's just u minus, that's the same constant A times v. Let's derive that and see where that comes from. Here's the orthogonal decomposition. We're assuming that we're starting with two vectors. So let's say we're given two vectors in our vector space. U and v belong to capital V. We want to know now, or address the question, how can we write or re-express one of those vectors, let's just say u. How can we write u in terms of v and w, where w, the second vector, is a vector that's perpendicular to v? Maybe I should draw a picture and see if we can, although whenever I draw a picture, that's always a little bit of a challenge. But let's say that that's supposed to be a line. Suppose that this is the direction of v, and maybe we have another vector. Oh, we do have a vector u. This is a 2D sketch, but it, I think, helps us understand what I'm trying to explain. If we now go orthogonal to v from that to u, this length is some fraction of v. That's our scaled version of v. And then we want to basically say, oh, u is av plus some w. And w is this vector that's orthogonal to v. That's all we're saying. And we want to know, how do we find a and how do we create w? That's what we want to build. And this generalizes to more than just 2 dimensions or 2 coordinates. This is for all coordinates, finite number. Let's first just say that we have some scalar a in one of our fields of numbers, real or complex. Now what we want to do is say that the vector u is some amount of v, and in fact we can actually say that the additional piece is just u minus av, where this is now the second vector w. And if you look at the right-hand side, all we're doing is adding 0 to u. So we really haven't changed anything. It's still u. U plus av minus av. But we've collected those pieces in a particular way so that now we've identified one piece in the direction of v, and we want to select a such that w is orthogonal to v. That's how we are going to define a. That's our goal. Our goal is now to find a that makes the vector v and u minus av, which is actually w. We want those 2 vectors to be orthogonal. And if we wanted to say this in a more shorthand way, we could say v is perpendicular to u minus av. Again, this is our w, and that's what we want. Now, if v, one of the pieces that's making up u, if v is perpendicular to u minus av, can we write that in terms of an inner product? Or how do we write that in terms of an inner product? If we know these 2 vectors, here's one vector, w, and we want it to be perpendicular or orthogonal to v, how do we write that? We just look at their inner product, don't we? We say wu is equal to 0. Thank you. wv. Getting ahead of myself. wv is equal to 0. But that is the same as u minus av inner product with v equaling 0. If that's true, now let's just use additivity of the first slot to separate out the terms in the first slot. And that says then that we have u and v's inner product, and then we have minus av with v, and that's equal to 0. But homogeneity in the first slot allows us to slide a out, the inner product of v with itself is just the norm of v squared. And we can now solve for a. We can put those terms on either side of the equal sign and divide by v, the norm of v squared, and now we can see that a is the inner product of u with v divided by the norm of v squared. And that's now the component or the fraction of v that we want to have in order to build up u as a combination of v, a fraction of v, and a piece that's orthogonal to v. Now we can rewrite our expression for u in the form that we had in the first part of today's class. We now have a, which is the inner product of u and v, divided by the norm of v squared. That's the a piece. That's av. And then we add to that the component that's orthogonal, which is u minus a, times v. Again, this piece right here is a. Again, we could draw that pictorially or graphically. If this is now v, then we are saying go to some fraction of that. Let's say it's av. Maybe I'm getting ahead of myself drawing that first. Maybe I should have drawn this. Let's say this is now u. And now what do we want? We want to take u and subtract a times v, and if we did that, we could say, oh, here's u, and now we subtract, so I'm now parallel with v. This is now minus av, and that gives me this vector, which is this same vector right here. If I'd drawn it properly, this is now u minus av, where a is this uv inner product divided by v squared. And now we can see that av plus u minus av gets us to u in this graphic. So that's the orthogonal decomposition. That's one of the pieces that we are going to continue to use over and over and over again. Let's now go into a crime scene and investigate. Let's talk about the Cauchy-Schwarz inequality. So now we have Cauchy-Schwarz inequality, or CSI, if we have two vectors, u and v, that are in capital V, then we have the following relationship. We can say that the inner product of u and v, its absolute value, is bounded above or is less than or equal to the norm of u times the norm of v. And the only time that we will have that inequality being equality is if one of those vectors, or if they're scalar multiples of each other. Equality if and only if u and v are scalar multiples. That's one way of writing the Cauchy-Schwarz inequality. We could also remember what this absolute value sign does for us, and we could say, oh, if I say that now I allow this to just be the inner product, then that's bounded above by u and v, and it's bounded below by the negative of u and v. That's just the definition of the inner product. I'm sorry, that's just the definition of the absolute value. So we could write the Cauchy-Schwarz inequality either as the blue line or as the black expression. Let's convince ourselves or see where that comes from. Again, this is all just talking about vectors now that we've defined an inner product, and we're using our definition of a norm using the inner product. And we haven't said anything about what the inner product is. We just say it exists, or we have one. Now, let's take two vectors, u and v, in our vector space, capital V. If we look at, well, let's just look at the easy case. Suppose that v is actually equal to 0. Is this inequality relationship true? Is the inner product less than the norm of u and the norm of v, or is it greater than the negative of the norm of u and the norm of v, if v is equal to 0? We know 0 is orthogonal to everything, so the inner term is 0, isn't it? And the norm of 0 is 0, so we have equality. So we know that if we had the 0 vector, this relationship is fine. So now we need to look at what happens when we have a non-zero v. If v is not equal to 0, like I said, now we can go back and start breaking up v into, or u, let's say, in terms of its orthogonal pieces. So if v is not equal to 0, we can decompose u in terms of v and w. Again, w is in our vector space. Where we are going to assume or have that w and v have an inner product of 0, or that w is orthogonal to v. And we know we can decompose u in that way. We just did that with the orthogonal decomposition, which says then that we can rewrite u. Again, we're starting with two vectors, u and v. Let's now separate or decompose u into a, and we're going to select a the way that we learned how to select it, the inner product of u and v divided by the norm of v squared times v, and let's just keep track of w. W is that u minus av, but we don't really need to say anything more than just w for now. Let's now that we have this, we can use the Pythagorean theorem to find a relationship between the norm squared of u. Meaning, if we had u, that's the same as av plus w squared by how we've written u. But remember the Pythagorean theorem. If these two vectors that are adding together are orthogonal, we can say that's equal to AV norm squared plus W norm squared. Let's now do that, and let's go ahead and rewrite A in all of its expressive form. We have the inner product of UV over the norm of V squared times V squared plus the norm of W squared. This piece is just A. And A is a scalar. And we can rewrite all of these norm squareds in terms of inner products. So that now if we pull out that A from the first term on the right, we can now say that that's going to be the absolute value of A squared, and we now have V comma V, since that was the inner product of AV with itself, and we're pulling A outside, and then we have plus W squared. But this piece right here is V squared. And now we have, well, maybe I should have done this in a couple of steps. We now have UV and now V squared plus W squared. And that's still equal to the left-hand side, which is U squared. That first term can be simplified a little bit. We can cancel two of those V square, or V, norm of V in the denominator, and just have one norm of V term in that rightmost term on the right-hand side of that equality. We have 4 in the bottom and 2 up top. Let's just keep 2 downstairs, so that now we have U squared is equal to the absolute value of UV squared over the norm of V squared plus W squared. Now we're going to basically throw something away, introduce the inequality. What do we know about this piece in terms of its size or its properties? Do we see that this is just numbers? This is a number on the left equal to the sum of two numbers, but what do we know about that rightmost number, which is the norm of W squared? It's never negative, is it? It's non-negative by the positivity of our inner product. This is non-negative by the positivity property of our inner product, which means if we throw that piece away, we know that the left side is greater than or equal to the piece that's left over on the right side. Writing that, we now know that U squared is greater than or equal to the absolute value of the inner product of UV squared over V squared, or the norm of V squared. If we now multiply both sides of this result by the norm of V squared, we're getting right next to our final result. Meaning, we can now say that this leads us to the norm of U squared times the norm of V squared is greater than or equal to the absolute value of the inner product of U and V squared. And that's really what we wanted. We know all of those terms are positive, so we can take the square root of all of those terms. And now we know that the absolute value of u, of the inner product of u and v, is less than or equal to the norm of u times the norm of v. And what did we have to impose on our inner product? Or what kind of an inner product did we state? Or did we? We never did we? So this proof, or this result, didn't require us to define an inner product. This required no definition of the inner product. Again, if we now play with this concept of an absolute value, then we know that minus the norm of u times the norm of v is less than or equal to the inner product of u with v, and that's less than or equal to the norm of u times the norm of v. That's coming just from the definition or the property of the absolute value. What if we now divide both sides, or all three terms, by the product of the norm of u and v? What do we end up with on the left? If we divide that by the norm of u times the norm of v, minus 1. So now we have minus 1 is less than or equal to the inner product of u with v divided by the norm of u times the norm of v, and this is now less than or equal to 1. We now have a quantity that's bounded between 1 and minus 1. Another quantity that has that same characteristic is the cosine of an angle theta. And this now can be used to say, oh, this is now this expression of the inner product of u and v divided by the norm of u and the norm of v is really giving us an angle between u and v. So this is now the angle between the vector u and the vector v. So that if we rewrote this and just said, oh, the cosine of theta is equal to, we're saying that that's now this inner product over u v. Now this is where you could now just multiply both sides through by the norm of u and the norm of v and see that the inner product is the norm of u times the norm of v cosine of theta. If you were wondering where that relationship might come from, now you have it from the Cauchy-Schwarz inequality. See how we're getting a lot of stuff now coming out of just some very basic concepts of an inner product. Now we have an angle between these vectors, and we have a way of relating their inner product, or the size of that inner product, to just the norms of those two vectors, the product of norms. Let's now look at what happens if we were taking the sum of the norms, and that's now leading us into the triangle inequality. Here, if we have two vectors, u and v, in our vector space V, then we know that the norm of the sum of u and v is going to be less than or equal to the norm of u plus the norm of v, where we will have equality if and only if these two vectors u and v are non-negative scalars or scalar multiples. Which means that u is equal to AV, for example. Well, these proofs have been kind of fun, so let's just keep going. Let's show ourselves where that's coming from. Suppose we now start with two arbitrary vectors in our vector space V. What's another way of writing the norm of this sum squared? How do we write a norm squared expression? What's another way of writing it based on Chapter 6 material? Not intellectual property, but inner product, right? So now we can take this as the inner product of u and v with itself. And now we can just go to town. Now we can start using additivity of the first slot, and that now becomes u inner product with u plus v plus v inner product with u plus v. But what do we know about the second slot? Is there additivity in the second slot? We showed that. So now let's write this. We now have u with u inner product plus u with v. That's from the first piece. And let me write the second piece in red, which is now v with u plus v with v. Those are the two pieces of each of those two terms. And now let's rewrite this piece. Let's flip those slots, or flip the vectors in the slot, and what does that produce? If I change the slot locations, it's not just uv, since I'm dealing with the generic case. I now have to take the complex conjugate. Let me reorder those a little bit. Let me say I have u and u inner product and v and v. So now I'm taking the first and the last term in those four terms, and I now have u and v plus u and v conjugate. What do I know about a number plus its complex conjugate? The imaginary component goes away, doesn't it? And I'm just left with twice the real piece. So I can rewrite this as the norm of u squared plus the norm of v squared plus 2 times the real part of the inner product of u with v. But now let me just use this concept of a complex number. And first let me write down the first two terms. I still have u's norm squared and v's norm squared. But what do I know about the real component of a complex number relative to its length, the complex number magnitude? And I've already shown it to you because I've already included the less than or equal to. We know that 2 times the real is going to be less than or equal to 2 times the length of that complex number. So this is now 2 times the absolute value of the inner product of u and v. There I'm just using the fact that the real component of z is less than or equal to the length of z. And I have equality if there's no imaginary component. Now what do I do? Well, now I have this. It's almost like we're doing a CSI, aren't we? We're a detective. We're trying to build this result. And now, if we go back and use CSI, we can bound, again, that absolute value. We have an upper bound on the absolute value of that inner product. That's now the norm of u squared times the norm of v squared. Let's then insert another less than or equal to, so that what did we start with on the left? On the left, way up there, was the norm squared of u plus v. Let's go ahead and write that down. We now have the norm squared of u plus v. That's less than or equal to the norm of u squared plus the norm of v squared plus 2 times the norm of u times the norm of v. And this substitution right here is from the Cauchy-Schwarz inequality. And now we just have to go back to our first algebra class. Whoops. Can't start dropping squares, can I? Well, I could, and then we might break something. But do you recognize that as the norm of u plus the norm of v quantity squared? This is now the norm of u plus the norm of v quantity squared. Or we've now derived that u plus v, the norm of that vector squared, is less than or equal to the norm of u plus the norm of v, that sum squared. Both pieces under the squared are positive, so we can take the square root and end up with the triangle inequality that we were trying to derive. Again, I asked the question, what did we have to do with the with this result? Did that depend on how we had defined the inner product? No. And we've talked about defining many different inner products for different vector spaces. And so these particular results hold for all of those inner products that we might want to define. And this is called the triangle inequality for a reason. And so we might as well just remind ourselves of a triangle. If we sketched a triangle in 2 dimensions, then we could say, oh, let me have the length of, or let me draw u and v. So here's u, and there's v, and this is u plus v. And we know that for any u and any v, that the length of u plus v is less than or equal to the length of u plus the length of v. And that might be one way that you try to remember this relationship when we're talking about summing the norms of 2 vectors. We know that the sum of the lengths is greater than or equal to the norm or the length of the sum of those 2 pieces. Here's one that maybe you haven't seen before. Another relationship, which is called the parallelogram equality. Not inequality, but equality. So here's the parallelogram equality. It says that if, again, we have two vectors, u and v, in a vector space, then if we take the sum of those two vectors and find the norm and square it, and then we take the difference between u and v, find its norm and square that, that's going to equal 2 times the norm of u squared plus the norm of v squared. Have you seen that before? Yes, no, no. Now, one way to remember this is by sketching a parallelogram or just thinking of an envelope. So if somebody's saying, well, what in the world are we talking about? Let's draw a u, and let's draw a v. And where is the vector u plus v? Well, it's just taking the tail of u and connecting that to the tip of v, isn't it? That's u plus v. That one's easy. So here is u plus v. Where is u minus v? Well, if we go to u and then we subtract v, then we're just going this way. There's minus v, isn't it? And so now u minus v is right there, isn't it? This is now, maybe I shouldn't have drawn in highlight. This is u minus v, but this is looking pretty ugly, but I hope you can sketch it better than I can. Let's say that we now had v there, which we could draw, and this is u. Do you see that this green u minus v is the same as that vector if I had sketched it properly? This is now u minus v. So now think of a back of an envelope where you have sort of these connecting these two corners of a parallelogram. And now you can say that the norm of one of those diagonals squared plus the norm of the other diagonal squared is 2 times sort of if you would walk around in a sense, but you're squaring those lengths, u squared plus v squared, and then you add those up again. That's the parallelogram equality. Well, I was having so much fun proving those others. Let's keep going. So let's prove that, since these haven't been too difficult, have they, to prove. So now let's start with u and v in our vector space v, and start with the left-hand side, which is the norm squared of u plus v plus the norm squared of u minus v. And we know how to write those norm squareds as inner products. We now know that we have u plus v with inner product with itself, and we have u minus v inner product with itself. And we have this down as far as additivity of the different slots. If we say, let's use the additivity in the first slot, in both of those pieces, we have u with u plus v with u plus v. And we then have plus u minus v minus v u minus v. Now keep me honest, make sure I'm not copying something down or writing something wrong. What do we know about additivity of the second slot? Is it true? So now each of these can be written into 2 because we have additivity of the second slot. So that now the first term on the right becomes u with itself, inner product, plus u with v. Then the second piece on the right, or inner product, becomes v with u, inner product, plus v with v. Then the third piece becomes u with u minus u with v. And finally, the last piece becomes minus v with u minus a minus v with v. And I see that this one cancels that one. And I have a u with v inner product canceling. And what am I left with? I'm left with 2 u's and 2 v's, so that's actually what I wanted. I now have u squared, 2 of those, plus 2 of v squared. Or I now have the 2 times u squared plus v squared. And you know what I'm going to ask now. How critical did this result hinge on an inner product? Didn't, did it? I didn't have to go in and specify a particular inner product. Again, I can answer or say or note that there was no definition of an inner product. So now we have Cauchy-Schwarz, we have triangle, and we have parallelogram equality. Now let's go in a little different direction. Let's now talk about the concept of orthonormal basis. Now that we've learned how to create things with these norms and these relationships, now we should be comfortable with normalizing things or dividing by norms. And that's what we're going to use to create these orthonormal bases. Here we call a list of vectors orthonormal if the vectors are all pairwise orthogonal. And we know what orthogonal means now that we have this inner product. So we look at each of these vectors in the list and we pair them up and we take the inner product, and it's 0 for all of these pairs of this vectors in the list. And we need them to be, they're ortho. Now we need them to be normal, to have a length or a length of 1. And each vector has a norm of 1. That's what we mean by a list of orthonormal vectors. They are pairwise orthogonal, and if I just look at one and find its norm, it's going to have a norm of 1. We could state it a different way. We could say, in other words, given a list, let's say that list is now E1, E2, and these are now vectors. These aren't coordinates of vectors. It gets a little confusing maybe, but these are now vectors. And there's my list of Michigan vectors. The list is orthonormal if I looked at the inner product of E sub I with E sub j, and that's going to be what I'll call this Kronecker delta. Delta subscript with ij. Where that new Greek symbol with the two subscripts just means it's either 1 or 0, and it's 1 when the subscripts are equal, and it's 0 when the subscripts are non-equal. That's what I'm meaning by that Kronecker delta. So delta sub ij is either 1 or 0. It's 1 if I equals j, and it's 0 otherwise. Pardon? So now we're not talking so much about a matrix just yet. So the question was, does this represent a diagonal matrix? We are just now looking at a list of vectors that are supposed to be orthonormal. If you now take a pair of those vectors, 2 at a time, and form their inner product, then the only time you will get a non-zero answer is when you have the same vector in the 2 slots. That's really all we're saying. And the non-zero inner product will actually be 1. Now, we're not talking about how do we interpret that any differently. Right now, we're just looking at this list of vectors. So we haven't really built a matrix out of those vectors. We just have a list, because little m could be 3. It could be 5. It could be 10, and we aren't yet collecting those. And little m, if m was 3, maybe these vectors have 10 coordinates, and little m is 3. So we really can't talk about an identity matrix. Is that clear? So the e's could be 10 tall. They could have 10 rows, and maybe we only have 3 of those. But we could still have a list of 3 orthonormal vectors that are in R10 or C10. That's all we're saying so far. But we aren't discounting the usefulness of these vectors. They're very useful. Which means I'm going to say that. Orthonormal lists are particularly useful. And if that's the case, then there must be all sorts of propositions associated with this. All right, so let's look at one of those. Proposition 615. That says that if we have a list of m of these orthonormal vectors, so now I have a list E sub 1, E sub 2, E sub m, And this list is now orthonormal. And it's in our vector space V. So that's what we're given. We have Michigan vectors that are orthonormal. We have this list. Now what we want to look at is what is the norm squared of a scalar sum of these vectors. Meaning, what if I take A1 times E1 and a scalar A2 times E2, and I just keep scaling all of these M vectors by a different scalar, and now what's the norm squared of that sum of vectors? And what is this? Now I can write a lot of vectors. I haven't yet said that M is such that it forms a basis, so I can't say that I can represent any vector, but I can write a lot of vectors as a linear combination of these M vectors. I can now say U, the norm of that squared, if I've now represented U as a linear combination of these M vectors, can I come up with a cleaner or a fairly quick way of telling what the norm squared is? And in fact, I can. I can say that all I have to do is take the absolute value of each of those scalars and square it and add those up, and that's equal to this. Meaning, this norm of that vector squared is equal to a sub 1 squared plus a sub 2 squared, etc., down or all the way through the absolute value of the scalar a sub m squared. And this is true for all scalars, a1, a2, a sub m, in our field. And you know what we're going to do now. Now we're going to prove that. Because you want to be able to, that's a good result, isn't it? That's a nice result. Well, the question was, is this some kind of variation on the triangle inequality? You could maybe think of it that way, but now I would say that we've really specialized our vectors now. Our vectors now, or at least our list of vectors that we're talking about, are orthonormal, and that buys us a lot. So now let's look at what that, or let's see where this comes from by proving it, or basically convincing ourselves that indeed this relationship is true. Let's start with the original expression. The norm squared of a1 e1 plus a sub 2 e sub 2 down to a sub m e sub m. And again, we haven't said anything about m and its relationship with the dimension of the vector space that we're playing with. But how do we rewrite this norm squared? This is just a vector, isn't it? You could say this whole thing is a vector u. So this is just the inner product of u with itself. That's how we get a square of a norm. Let's do that. So now I have to write this again. I'm going to have writer's cramp. a1 e1, a2 e2, plus a sub m e sub m, inner product with that same vector. a1 e1 plus a sub 2 e sub 2 plus a sub m e sub m. Now, you all know how to eat an elephant, right? You know how to eat an elephant? One bite at a time. So this is kind of a mess, but we can just crunch through it. What do we know about that left? Well, that's just a sum of a bunch of things in the first slot. And what do we know about the first slot and sums? Additivity. So let's just do the additivity with that first slot. So that now we can say, oh, the additivity of the first slot, and let me just do this, collapse this down a little bit. Let me say that I'm going to sum from L equal 1 to M, and I now have A1, E1 with this rightmost slot. So that now I have A sub L, E sub L. Plus this sum, and can I use the same index, L equal 1 to M of A sub 2, E sub 2 with A sub L, E sub L. Is that okay? And what else do I just keep doing that. Thank goodness for these collapsing notation with the summation sign. So now I have the sum from L equal 1 to M of the last one, A sub M, E sub M, with A sub L, E sub L. That's just the additivity of the first slot. But I can collapse that down a little bit because it sort of looks the same in the first slot if I just summed over those indices. Now I have basically a collection or a set of sums, two sums. Now I can say that this is equal to this sum from, let's say, K, and my K's are not very nice. I can't seem to write a K very well. But now inside that I have each of these sums from L equal 1 to M of this is now A sub K, E sub K. This is A sub L, E sub L. That's just compacting the expression. And in this age of recycling and efficient use, we need to compact. So now we've compacted this expression. Now what can we do? We have some scalars sitting inside an inner product. What do we know we can do with those scalars? The A sub K is in the first slot. What do we know about the first slot and homogeneity? It just slides out. What about the second slot? It's the conjugate. So now we can apply our homogeneity of the first slot and our complex or our conjugate homogeneity of the second slot to end up with writing this as this sum from K equal 1 to M and a sum from L equal 1 to M of A sub K, A sub L conjugate times, E sub K inner product with E sub L. And that's just using homogeneity. But what do we know about the inner product of E sub K and E sub L? A lot of those start falling away, don't they? The only time we have any non-zero result from the inner product of E sub K with E sub L is when K and L are equal. That now gets rid of one of those sums. So that now I can collapse this down and say that I now have the sum of, maybe I'll stick with the L's, A sub L star, L equal 1 to M. Does everybody see where that came from? That's the Kronecker delta relationship on the orthonormal vectors E sub I, or E sub K and E sub L. That only is 1, and it's equal to 1, so it basically is sitting right here, but I'm not even going to write it. And now what do we know about A sub L times its conjugate? This is now x plus jy plus, or times x minus jy. That will end up being x squared plus y squared, which is just the norm or the absolute value of a sub l squared. So that this is now the sum from L equal 1 to m of a sub L squared. And what in the world is that? Well, that's exactly what we were trying to show. This is now a sub 1, absolute value squared, a sub 2 squared, all the way to a sub m squared. So now, if you have a list of orthonormal vectors and you want to write another vector in terms of those, and if you want to start thinking about the norms are pretty easy to compute. Now we just have to worry about the absolute value of the scalars and squaring those and adding them up if we wanted the norm squared. Now let's look at what another property. So now we know about the sort of the length of vectors that are made up of orthonormal vectors. Let's look at a corollary, which is corollary 616, which says the following, that every orthonormal list of vectors is linearly independent. And remember, this list doesn't have to be a full list. Maybe I have a 10-dimensional space and I just have 3 in my orthonormal list. Those 3 are still linearly independent. So now let's just look at this proof. Let's take now a list up to little m, Michigan. So take this as our orthonormal list. Now, suppose that we can write or find scalars, a sub l, such that the sum of those scaled m vectors is equal to 0. So let's say that let's write a1 e1 plus a2 e2. So this let's write says that I can find scalars such that that's the case. But now what do we know from our previous proposition? From the previous proposition, proposition 615, we can say something about the norm squared of that vector on the left, and we know what the norm squared of 0 is. So the 0 vector shows this means that the norm of 0 squared is just 0, but if we looked at a1 e1 plus a sub 2 e sub 2 plus a sub m e sub m, and we took the norm of that squared, what do we know about that norm squared? That we can find by taking each of the absolute values of the scalars and summing their squares. So that's now a1 squared plus the absolute value of a sub 2 squared, etc., plus the absolute value of a sub m squared. But if that's equal to 0, what does that say about the a sub i's? They all have to be 0, right? Or they could never equal 0. If we take the absolute value of a scalar, the only way that any of those can sum to 0 is if they're all 0. So this implies, or which means, all a sub j's are equal to 0. And now if we go back to this relationship and say, oh, the only way that this can equal 0 is with all the scalars equaling 0, what does that tell us about the vectors E1 through En? This is why all of this is starting to fit together. Now we know those vectors, which we just started as orthonormal list, those are actually linearly independent. And we'll have to quit having so much fun, and we'll pick up at that point on Wednesday.